Hi everyone, my name is cfyee from Keysight. The title of my presentation today is En route to PCIe 7 chip-to-chip PHY compliance at 128 giga transfer or gigabit per second speed rate. Content of sharing today is the intro of PCIe 7 and PAM4 and key design consideration for PCIe 7 physical link or PHY. Next, analysis and result, and then wrap up with a summary. Intro of PCIe 7 and PAM4. PAM4 signaling has 4 digital amplitude levels. It has greater benefit over the conventional PAM2 signals. Each symbol in PAM4 consists of 2 data bits that give twice as much data throughput for the similar baud rate. For example, 64 gigabaud is equivalent to 64 gigabit per second in PAM2 and 128 gigabit per second in PAM4. PCIe generation 1 to 5 was implemented in PAM2, whereas PCIe generation 6 and 7 applies PAM4. PCIe 7 spec at 128 gigabit per second was released by PCI SIG in 2025 to fulfill the industry requirement for a higher speed and lower latency connectivity. Typical PCIe 7 link topology on digital board is shown below. Microstrip or outer PCB layer route versus the stripline inner PCB layer route. Chip-to-chip PHY, including the BGA package, has total loss budget of 36 dB at fundamental frequency 32 GHz. Next, key consideration for PCIe 7 filing. First is the choice of laminate material. PCIe laminate materials are classified based on the dielectric properties of loss tangent DF and dielectric constant epsilon R. Referring to table above, the standard loss material has DF above 0.01, low loss material has DF 0.002, and ultra low loss material has DF 0.001. Dielectric loss is directly proportional to DF. Previous study already showed that the standard loss material is too lossy, is not suitable for PCIe generation 4 and above. Analysis is done on low loss versus the ultra low loss material if applicable for PCIe 7 filing with 10-inch routing, which is a typical digital board system distance. Next, mitigating the signal impairment due to via. Via structure is built with via hole, pad, and clearance. Parasitic capacitance is directly proportional to the hole and pad, whereas the parasitic inductance is directly proportional to the clearance. Impedance matching is achieved by optimizing the via when capacitance is balanced out by the inductance. Next, mitigating the signal impairment due to the capacitor footprint. AC coupling capacitors are placed in series with the PCIe signal tracers to safeguard the input voltage fault condition. The mounting pad of the capacitor is wider versus the signal trace on PCB. For example, capacitor with O201 package is 10 mm wide, whereas the 01005 package is 8 mm wide. Signal that travel along 7 mm wide trace experience the capacitance impedance discontinuity upon reaching the mounting pad. Transmission loss performance for mounting pad size 0201 versus 0105 is studied. Next, analysis and result. Loss performance comparison between laminate materials. 4 differential transmission line models with 10-inch length and 85 ohm impedance is studied. Microstrip 1A with micron 6 and microstrip 1B with micron 7 and stripline 1C with micron 6 and stripline 1D with micron 7. SDD21 or insertion loss at fundamental frequency 32 GHz experienced by model 1A, 1B, 1C, and 1D is -7, -6, -8, and -6.5 dB respectively, which is well below the 36 dB loss budget in the PCIe 7 spec. Chip-to-chip full path channel simulation is carried out to ensure the implementation viability of the low loss Micron 6 in PCIe 7 communication, which is more cost effective versus the ultra low loss Micron 7. Next, via optimization. 5 different via models are varied with dimension of hole, pad, and clearance. Model 2E with a 6mm hole, 10mm pad and 40mm clearance diameter is the most optimized, which is 4.8% impedance mismatch and 0.22 dB at 32 GHz. Next, capacitor dimension comparison. Model 3A with 0201 capacitor in series with 7mm trace width, while Model 3B with 0105 capacitor in series with a 7mm trace width. Model 3A encounters 3 ohm capacitive impedance discontinuity, whereas the 3B experiences a smaller capacitive impedance mismatch of 0.8 ohm. Model 3A encounters more severe wideband transmission loss around the frequency 10 GHz, delta 0.1 dB, 42 GHz around 0.2 dB, and 80 GHz around 0.3 dB versus Model 3B, due to a larger mismatch impedance that contributes to the worse signal reflection. Next, PCIe 7 chip-to-chip channels analysis at 128 gigabit per second. The chip-to-chip file analysis topology using ADS at BR 1 to the power of E minus 6 is shown above. BGA package S parameter models of chip A and chip B, PCB channel S parameter model, and IBIS MI model of chip A and chip B are cascaded to form the chip-to-chip file analysis. PCIe 7 PAM4 signals is injected by the IBIS MI model of chip A at 128 gigabit per second. The TX or transmitter chip A amplitude set as 1000 milliwatt and equalization preset Q4 with 0 dB pre-shoot 2 and pre-shoot 1, and also minus 3.5 dB and de-emphasis is activated for loss compensation, whereas CTLE and 29 tap FFE and also 1 tap DFE at the receiver chip B is turned on to compensate the channel loss. PCB channel is imported with 10-inch microstrip and strip line respectively. Model 4A represents the microstrip and 4B represents the strip line. TDR plot indicates the impedance mismatch below 5 ohm. Meanwhile, the ISWTA2026 plot indicates that the end-to-end link loss including the chip package is below 20 dB at fundamental frequency 32 GHz. On the other hand, the eye contour probe at the receiver indicates the smallest 111 milliwatt and eye height and 4.22 picosecond eye width for Model 4A, while 96 milliwatt eye height and 3.67 picosecond eye width for Model 4B. Analysis result meets the PCI SIG spec of the minimum 10 milliwatt eye height and 1.6 picosecond eye width before PCB prototyping. In summary, all the key pre-route signal integrity considerations explained in this paper shall be taken seriously to develop PCIe 7 chip-to-chip PHY on PCB, including the choice of laminate material and capacitor package size and re-optimization to achieve the minimal link loss and comply with the PCI SIG spec, paving the way for the seamless high-speed communication in digital board system. Analysis outcome shows impedance mismatch within 5% and ISWTA2026 below 20 dB at fundamental 32 GHz, meeting the PCIe 7 PHY standard. That's all for my presentation. Thank you.